Okay. Yes, good morning, everyone. Thank you for organizers. It's very exciting to talk here. So I'll talk about integrality gaps for sparse Bernoulli hypergraphs. And this is so this is a joint work with 3 other PhD students. So Gabriel Arpino from Cambridge, Rafael Barboni from ENS, and Nicola Grametto from Princeton. Okay, so first I'll present the model and give some examples for the model, some motivations, and then show the related work from statistical mechanics community, and in the end our results and our conjectures of the open problems. So let me just start directly with the problem formulation. Let's say I have the matrix A, which is m times n matrix, and each entry is 0, 1. Then I want to find the vector x of minimal norm such that x belongs to 0, 1. So it's n-dimensional vectors with 0, 1 entries, and ax is greater or equal than 1 entry-wise. So this is an integer program. I call this, denote this as IP, and I want to analyze the value of this problem. Value of IP, so the lower and upper bounds for the integer program will be my point of my talk. Okay, now what this problem actually represents. So I'll give some examples. First, you can think of this as a hypergraph. So n will be number of vertices. M is number of hyper edges. And then in this formulation, this problem is exactly the hypergraph vertex cover. Okay, just to remind you what is the vertex cover problem. Let's say now we restrict ourselves just to graphs, standard graphs. So in my matrix, for my matrix A, as I said, M is the number of hyper edges, N is the number of vertices, and so each edge is represented as a row, and if I have 1 in entry ij, that means that the vertex j belongs to hyper edge I, right? And if I want to restrict myself to the standard graphs, then I just have the additional constraint that for any I, the sum over j, any ij is equal to 2. And this is the vertex cover problem. And okay, just to remind you what's the vertex cover problem. So I have a graph, some graph, and I want to find I want to select the vertices such that each edge has one of the endpoints among these vertices. So for this graph, for example, I select this vertex which covers these 3 edges, then this vertex which covers these edges, and I guess this vertex. So for this graph, I need to select 3 vertices to cover it. Okay? But now we remove this constraint, and then we think of hyper edges, so there's no constraint on the size of the edge. Okay, so that's the first example. The second example is the heating set problem. So here I have the ground set M, and I have the family of n subsets. And I want to select the some subsets from this family so that they cover the ground set. Okay, that's exactly the same problem. And also, I mean, now the connection to the previous talk, to Noella's talk, is you can also think of this as the group testing problem. But now you don't have control over the tests. So here the n is the number of individuals and m is the number of tests. And you don't construct the tests, but you have already the results of the tests, and then you want to understand what is the smallest number of positively affected people in the among the individuals. Okay, is it clear? Okay, so now.
The modulo the fact that the group testing is an inference problem.
Yeah. It's just analyzing the size of the yeah. It's not about inference. Okay, so now the related work. So there is work by Dmitriev and Marco Terzi from 2007. When they analyzed the same problem, but in particular regime. So now we have random L regular K uniform graph. So hypergraph. So this means that so L regular means that the degree of each vertex is equal to L, and K uniform means that the size of each edge is equal to K. And they looked at the setting, so at the thermodynamical limit, so n goes to infinity, n over m goes to some constant. And okay, K and L are fixed. And I have this some diagram. So here is K, so it's edge, and here is L, so it's the vertex. I mean, degree and size of edge. And the diagram goes something like this. So here is a simple case, replica symmetry case. Here is one RSB, and here is something full RSB. So K, for example, K equal to 2 corresponds to this. So we just have a standard graph. And for K equal to 2, it's known that the vertex cover problem is NP hard. So, and okay. So now what is our setting? We also look at the random hypergraphs, but now it's not a regular, it's a Bernoulli hypergraph, so each entry of the matrix is ID Bernoulli. So we have n going to infinity, we have some parameter delta, and for us the probability p scales as n to the minus delta, and m scales to as n to the delta log n. Okay? So we actually analyzed here, we also look at n to the delta log epsilon n, and then we have a second parameter epsilon that varying which you can see different effects. But for this talk, let's just assume, we'll just look at this case. Okay, so just to show what's the connection here. So in our model, first number of so edges grows sublinearly, right? Then the degree of each vertex is arithmetically on expectation, but the size of the edges grows also polynomially, so quite fast. Okay, but since the degree is logarithmically, it's still we call it sparse line. Okay, and then we want to understand what happens in this case. Okay, so what are the results of the conjecture? So what we want to look at is the value of IP, both from upper and lower bounds. Because IP in general is hard to solve, so one way to approach IP is to look at the relaxation. So we can look at the linear relaxation. I'll write it down. Oh, yeah. Just I allow my x belonging to, so it's IP, but instead of with x in 0 and 1. So, okay. This can be efficiently solved. And of course, since this is a relaxation, I always have this lower bound, value of LP. Okay, so what we are able to show is, first of all, the lower bound here. So we show that LP up to a constant is bounded by n to the delta, right? Oh yeah, when people study these relaxations, one question that you ask yourself is what is the gap between IP and LP solution? So IP gap, which is equal to value of IP divided by the value of LP. So for this, you need also to upper bound this, and there is a very simple upper bound. So there is a simple upper bound. It's just saying that the value of IP is upper bound by m number of constraints, number of hyper edges. Why? Because you can just go through your graph edge by edge, and just for each edge you pick something. But in our setting, this is already n to the delta log n. So this is already, this gives a good bound, but okay, I'll say the conjectures that we have. Yes. Okay. So for the conjectures, we have two conjectures over here. So the conjectures 1. So first we, from the experiments, from what you see, the conjecture that the value of LP grows as the value of IP and actually grows as n to the delta. So this, this very simple bound is actually a bit loose by logarithmic factor.
So what does IP stand for?
Sorry, IP is the solution for this problem.
Integer program.
Yeah. Yeah. LP is the new problem. Okay, and the conjecture 2 is that so there is a very simple algorithm called greedy algorithm, and the value of the greedy algorithm divided by the value of integer program is also converged to 1. So the greedy algorithm is a simple heuristic to find this this cover. Just you go vertex by vertex, then find the vertex which covers the most number of edges. You take this vertex into your solution and remove these edges that are covered, and then repeat. So yeah. Okay, so these are our two conjectures, and just to comment a bit on also connection to this work is that so here in this setting, what we observed is that the greedy algorithm actually performs worse. So there is a gap between the greedy algorithm and the belief propagation that they ran here. But in our setting, we don't observe something like this. Okay, so I think that's going to be it for my talk.
We have time for a few questions.
So you're saying there's polynomial sum algorithm, so the greedy procedure can give the value. Is that true for all the values of the parameters? There's no hard phase in this problem?
So I think, I mean, in this setting there is, but for us, I will look at this setting also by varying epsilon. So in this setting where there is the same n to the delta in the NNP, so it's important. But if the epsilon, we can vary it, but still we get the same setting.
So if you change the deltas in the P and M, then
probably yeah, something will change. But yeah.
Any other questions? If not, thank you very much again.